Water is the driving force behind many biological functions and chemical reactions on Earth. Water is a polar molecule with a net negative charge around its oxygen atom and net positive charges around its hydrogen atoms. It has a bent shape with an angle of about 105 degrees. These characteristics give water many unique properties, one of which is the ability to be very attractive to itself. Hydrogen bonding describes how the positive ends of water attract the negative areas to create strong intermolecular forces. Because water has strong attractive forces with polar molecules, water will pull other water molecules toward itself while excluding non-polar molecules like oil. These interactions are called hydrophobic and hydrophilic interactions. Hydrophobic means water-fearing, and hydrophilic means water-loving. You may have witnessed the results of hydrophobic and hydrophilic interactions if you've ever had your salad dressing separate into two parts, an oily phase on top and water and other water-soluble parts on the bottom. Hydrophobic and hydrophilic interactions are useful properties in chemistry when you want to collect a product from a mixture of water and oil. All you have to do is wait for the phases to separate on their own, no energy on your part required, and take out the phase you need. This same principle is also used in chemical engineering on a larger scale in simple extractions. Not only are hydrophobic and hydrophilic interactions important in chemistry and chemical engineering, they are also essential to biology. Proteins are very important in biology because they serve nearly every function necessary for cell life. Proteins destined for the cell matrix are built up by the ribosome and extruded into an aqueous environment inside the cell. When proteins are folding, hydrophobic areas of the protein tend to clump together towards the inside of the protein, while hydrophilic areas of the protein are attracted towards the outside of the protein nearest to the aqueous environment of the cell matrix. In other words, protein folding is governed by hydrophobic and hydrophilic effects. Phospholipid bilayers are also essential parts of the cell, governed by hydrophobic and hydrophilic interactions. Phospholipid bilayers compose cell and organelle membranes. These membranes create structure within the cell and allow for regulation of chemicals between the cell and the outside environment. Let's take a closer look. The pieces that make up the phospholipid bilayer have a hydrophilic head and a hydrophobic tail. These pieces arrange so that there is minimal contact of the hydrophobic tails with the aqueous environment. Without hydrophobic and hydrophilic interactions, we wouldn't see the same kind of protein folding and phospholipid bilayer formation that our cells need to survive. Therefore, the interactions between polar and non-polar species, the interactions between water and oil, are essential to life as we know it. Now that we have established that hydrophobic and hydrophilic interactions are so important, let's take a closer and more detailed look at what's happening between water and oil at a molecular scale. We know that water and oil do not mix, but they have to exist side by side at the line between the two phases. How do they do this? At the oil and water interface, water will arrange itself by alternating in opposite directions so that the net polarity of water approaches zero. With this arrangement, neither water nor oil will have an effective charge, allowing water and oil to exist stably next to each other. Another property that stabilizes the mixing of oil and water is coalescence. This is where droplets of oil within a water phase will come together to minimize the surface area between the oil and the water. As has been said before, when water is attracted towards other water molecules, oil is excluded from the mix. These hydrophobic and hydrophilic effects lead to very ordered structures like proteins and the phospholipid bilayer. But not everybody likes order, especially not the universe. The universe enjoys chaos, or in more scientific terms, entropy. Entropy is the number of positional states of a system. As you may imagine, it is difficult to picture every single positional state that every atom and molecule can adopt at any given time in a system. Thus, the definition of entropy is often simplified to chaos or disorder, so that we can begin to imagine what entropy would look like. Another way to look at entropy would be to imagine molecules completely motionless, locked in a perfect array. This would represent zero entropy. As the molecules start to move and stray from the array, entropy increases. So if the universe favors increases in entropy, why can there be very ordered structures in the world like proteins? This is because the ordering of proteins creates a greater amount of disorder to the surrounding water in comparison. Had the protein not folded so compactly, allowing hydrophobic areas to float around through the cell, water would have had to arrange itself in alternating opposite directions to cover a wider surface area. This arrangement orders the water, which the universe does not favor. Instead, the compactness of proteins minimizes surface area, thus minimizing oil and water contact. Thus, even though a protein is compact and very ordered, the disordering of water around the protein outweighs any order the protein added to the universe. This means that entropy of the universe increases, and the universe is happy. Now that we know all of this about hydrophobic and hydrophilic interactions, let's talk about one way engineers can use this knowledge to their benefit. One way that medicines and drugs can be encapsulated is through water and oil and water emulsions. Water, oil, water emulsions are used to protect the encapsulated drug and to allow for its controlled release. To start, water, oil, water emulsions are made by adding water phase containing a water-soluble drug to a larger amount of oil phase. This mixture is homogenized at high speeds to create small droplets of water inside the continuous oil phase. Then, the resulting water and oil emulsion is added to an even larger volume of water containing an emulsifier. Emulsifiers are molecules like polyvinyl alcohol that have both hydrophilic and hydrophobic ends. They are used to stabilize mixtures of water and oil by attracting both of them to itself. This stabilizes oil droplets in water and works to prevent coalescence, or the coming together, of oil droplets. This stable mixing of the two phases is the principle that soap uses to wash oils and grimes from your dishes or hands. Soaps are emulsifiers. As the water and oil and water mixture is homogenized a second time at high speeds, the emulsifier is responsible for preventing coalescence of the water and oil droplets. This creates capsules with a smaller size and even size distribution. To finish making the water, oil, water capsules, the oil inside the capsules is evaporated at low speeds using a stir bar. Then, the mixture is centrifuged to separate the hardened capsules from the water phase. The water phase on top is removed and the capsules on the bottom are lyophilized, or freeze-dried, to make a dry powder. So to recap, hydrophilic and hydrophobic interactions are important to biology and life. Our understanding of the complexities of these interactions has allowed us to use hydrophilic and hydrophobic effects to our advantage in separation and in medicine.